Good afternoon, ladies and gentlemen. Thank you for coming here, and it's my great pleasure to talk here at this wonderful city with this wonderful weather. Right, and the most wonderful thing, of course, here is the air conditioning about the weather. So I will talk about complexity of proofs and computations, and in fact, when I only started to prepare my lecture, I discovered that the most important thing when talking of this thing is to really decide what are we doing here, what are we celebrating. Are we celebrating the end of the century or the end of millennium? Because both proofs and computations are very ancient concepts, and as I will try to show you later, they started as a sort of a common thing, as a sort of the same thing, and in fact, the purpose, well, hidden purpose of my lecture is to try to convince you that now or at the end of either the century or the millennium, we are, at least in our science, theoretical computer science, we are a sort of witnessing, I don't know even how to call it, we see that the proofs and computations, they basically come together again. And there are already some things where you can't clearly say whether it is a proof or a computation, and blah, blah, blah. But anyway, so to be serious, I will just show you, as long as the millennium is concerned, I will just show you one slide, just to see how all this started, and then we will come to more modern things, and I will try to say something about the current state of this issue. Good. So, I'm not, of course, a specialist in the history of mathematics, so I can say something wrong, in which case I apologize. But it seems that when the mathematics only started, for example, in the ancient Egypt, then people really did not distinguish between proofs and computations. So they simply knew how to, how to sum fractions, or if they wanted the right angle, they knew how to construct it, just take 3 here, 4 here, or 5 here, but if you would ask them how to prove that what you are doing is correct, they simply would not understand the question. For them, mathematics was just a set of algorithms. And then, in the ancient Greece, mathematics first appeared as a deductive science, so people started to prove theorems. They were interested in more and more abstract things, and here is probably the most famous discovering of that period, or at least that's how it is usually illustrated. And on the other side of this picture, for a long time, there was no such thing as the theory of algorithms. So people really were not interested in this. So mathematics developed as an abstract science further, and more sophisticated concepts which have little to do with the reality appeared. Firstly, it was discovered that not all numbers are rationals. Then it was discovered that not all of them are positive, real, and so on. Things started to have less and less in common with reality. Sometimes, actually, I should admit that there were occasionally some there was some renewed interest in algorithms, but it was something really occasional. For example, when there are now famous formulas for solving equations of the third or algebraic equations of third and fourth degree were discovered in, 15th probably century, then it was really a set of rules how to solve these equations, and of course people did not bother that in most cases these rules lead to something meaningless from their point of view. And then in 18th century, for example, people were really interested in how to factor numbers, or how to prove, or how to show that some numbers are prime. And integration and differentiation also started, well, at least that's what the story says, it started with calculating the volume of bottles. So there was occasional interest in algorithms, but still mathematics until the turn of the century developed. It became more and more abstract, and finally, as we all know very well, it finally led to quite unpleasant things, like this Russell paradox. If you make a set which consists of all the elements X that are not elements of themselves, then you are immediately Okay, good. Thank you. Okay, so if you form this set, then you are immediately in trouble. Right, and Cauchy invented an example of a function which is everywhere continuous, but you cannot differentiate it at any point, and so somehow it was also, well, somewhat alarming for people, and it all somehow, the new period, quite the new period, it began around the turn of still this century. And it started with the famous Hilbert program. And that's where the story with algorithms started to continue. It continued because I don't want to say much about Hilbert's program. Some parts of it are not quite relevant to my talk. But one of the parts in this program was, we reduce all the mathematics to some game with abstract symbols, right? We invent some formal system to encode all our mathematical statements. Then we know exactly what a theorem is, and then one of the parts of this program was to discover an algorithm which would some algorithm which would immediately close the mathematics as we know it. That is some mechanical procedure. You give it a statement, and this procedure should decide whether the statement is a theorem or not. And of course, if you want to study these things rigorously, then you should know well what an algorithm is. I mean, you don't have to know it if you try to prove the existence of an algorithm, because if you have an algorithm, then everybody recognizes it. But if you want to prove negative things, then of course you cannot do it without an abstract notion, a formal notion of an algorithm. And the work on Hilbert program eventually led to the development of mathematical logics at some point, and these are famous Gödel theorems on incompleteness, and followed by other things. It became clear that it was proved actually that Hilbert's program does not work, but it was already too late. Mathematical logics started to develop anyway, and it already gained sufficient momentum, and that's why actually here all my arrows get straight, because so far it was something vague, something informal. Now we're talking about theorems, about definitions, in the sense we would recognize here. And there were two essential parts of mathematical logics, I would actually say, two most essential parts. The first part was the computability theory, what can we compute in principle, and another part was the proof theory, what can we prove with this or that logical means. And actually it was recognized, it was soon recognized that proofs and computations, they really do many things in common, and quite often when we argue about proofs, it helps us to argue about computations and vice versa. But somehow in the mathematical logics, there was no such sense of unification I will try to show you today. So still, logicians would say this is a proof, this is a computation, they can help each other, but these are two quite different things. And the situation started to change. Right. First of all, somewhere in the 60s, computability theory, at that time, real computers started to appear, and people got interested not only in the questions what can be in principle computed, but they started to think what can be efficiently computed, what can be really programmed on our computers. And that's where the computational complexity appeared around the 60s. And in fact, this arrow, I guess this is what Avi is going to talk about. I won't steal bread from him. But probably the most famous discovery of the computational complexity was the class NP and the related and the related P versus NP problem. Right? When you talk of the modern complexity, you cannot really miss this class NP. And it was discovered in the pioneering works by Cook, Karp, and Levin in around 1970. And once more, I will talk little today about purely computation aspects of all these things. But for the purpose of my talk, what is important is that NP was really the first example when proofs and computation, they really come together. And I will try to show you how it worked here, and also what it, where is this now? Right, so that's what, okay. That's the right, general direction of my talk, some overlying. Anyway. Okay, so let me very briefly recall a few basic definitions from the classical computational complexity. Right, it turns out that if you are interested in solving algorithmic problems, then without loss of generality, usually we can encode them as the problems of computing a mapping F from finite binary strings to finary binary strings. And one important subclass of this class of problems is made by so-called decision problems. Well, you have some sets of binary strings and you want to recognize whether a given string X is in this L, language L, or not. And each is, of course, it is just the same as computing the characteristic function of this language. Well, and 0 is usually interpreted as no, and 1 stands for yes. And it is not very important which computational model are we going to adopt. For historical reasons, the most popular model is so-called Turing machines, but it's really not important, so I even did not put here the exact definition. Well, anyway, our information is stored on some tape. Let me just say a few quick words about it. So we store our information on a tape. Each cell can contain a symbol from some finite alphabet, and we have a head, which also has some internal alphabet, and in every particular moment of time, it is in some particular state, like Q, and it looks at some cell on our tape, and depending on its own state and what it sees, it can either moves to the left or to the right. It can write here something, and it can change its internal state. It's not really important. And when something happens, for example, it comes to some distinguished state, the machine says, okay, that's it. What you see on the input tape right now is your output string. Right. I don't pay too much attention to that, simply for the reason that things are very robust, and you can take instead of Turing machines, at least on the level I will be talking today about, things are very robust, and you can actually take instead of this ordinary one-tape Turing machines, well, whatever you like, I don't know, Pascal language, whatever you like. It's not very important. All right, so if you have a Turing machine M and some input string X, binary string X, then we denote by Tm of X the working time, or just the number of steps the Turing machine M takes on the input X. It's working time when it works on the input X. And right. This concept, which probably was firstly considered in this paper, but maybe I am, okay. Sorry?
It doesn't look to me kind of concept. I thought it was known. People had to imagine it was not known to everybody who thought about it. Like Turing, for example.
You mean the...
In Neumann.
No, in the... You mean the worst case complexity?
But von Neumann was aware of all of that.
The worst case complexity, yeah?
Well, not this word, of course, if you read von Neumann, all these ideas are there.
Okay, so let me actually... Well, it makes...
Such a trivial mark how you attach names.
It makes sense.
Yeah.
Okay, good. It really makes sense. Well, it's okay. Let me put it more carefully. That's actually I recently was wrote something historical, and it's the first written source where I discovered it. Just this in this explicit form, and it was really used already in that paper. But okay, it's not important. Anyway, it's a very useful. It's a very useful concept because we cannot really study this function Tm of x because it behaves a sort of crazy. For some inputs x, the answer is very quick. It's something trivial. For other strings x, it is very big. It's really hard to study this function. So, but if you take this one more step, namely we denote by Tm of n the worst case complexity, that is, if you have a string x and you only know that its input length is at most n, and what is guaranteed by your algorithm, then actually this function can already be studied quite successfully. And of course, the next logical step we would like to take would be somehow to manage to define, of course, if we have a set of functions of natural on integers, then of course we cannot take the minimum of this function. We don't know what is the minimum of two functions, but perhaps we somehow can manage to do it, and we can define what is the best algorithm for a given computational problem. But Blum in '67 proved that it does not work. There are some problems for which there is no most efficient algorithm. If you have any algorithm which solves this problem, then you can always speed it up and severely speed it up. So the alternative way, which was taken actually by the complexity theory, was by introducing the concept of complexity classes. So we turn around this difficulty like this. Simply we fix some computational constraints our algorithms must satisfy. Well, and for the time being, we are interested only in this constraint. We have some function t of n, and we are interested only in those algorithms which work within t of n steps. And we form the complexity class, which consists of all functions of all algorithmic problems that have at least one algorithm from this class. And this is already quite a useful notion. And in the seminal papers, this hierarchy theorem was proved. It shows that that there is at least something to study. Well, in this framework, it means that if you take these classes with increasing complexity constraints, then you of course you have here the inclusion, but what is important that each is a proper. You can always show, for example, some algorithmic problem which can be solved in cubic time but cannot be solved in the quadratic time. And the last thing which was discovered in this pre-NP period is the class P, and this is the class of all functions, of all algorithmic problems that can be solved in polynomial time. So you fix the exponent k, and you take the union of all these classes for all fixed constant k's. And this class is actually considered as a very natural approximation to the class of efficiently solved problems that can be efficiently solved on real computers. And there are some exceptions to that, but anyway, I would recommend to see this source for a sourceful discussion of this matter. And this class was also proposed by several people as the class of approximations to feasible, computationally feasible problems, also in '60s. Okay, good. That was for the introduction, and now let's now come to the theory of NP completeness. So So when the class NP was introduced by Cook, Karp, and Levin, it completely changed the overall picture, because before that computational classes were classes which corresponded to computations on the real computers. It is very different with the class NP. There is no such thing as non-deterministic Turing machine in reality, well, so far at least. So, and a non-deterministic Turing machine, it works very much like the ordinary Turing machine, but with one additional feature. And as I just said, so far we don't know how to simulate this feature by any physical process. And the feature is like this. So if at any given moment of state, at any given moment, right, for example, recognized by the fact that the head looks at a cell where the question mark is written, it has two possibilities. It can branch either to the left and put here 0, or to the right and put here 1. So it is a branching state, and of course, if we have a non-deterministic Turing machine that it branches, and at the end we get a computational tree, and it is a binary tree, and the working time of a Turing machine will be the height of this tree, which means that the number of states of nodes in this tree is in general exponential, so we don't know how to simulate it by ordinary machines. But anyway, this still looks like a computation, well, a funny computation, but non-deterministic computation. And the acceptance conditions are these. If your string x is in the language L, if the answer should be yes, we require that there is at least one accepting computation. There is at least one branch in our, okay, so it's the time to use the second projector. There is at least one branch, I don't know, in your tree which leads to an accepting yes state, and if x is not in the language L, then there is no such branch or no such path in our tree. And NP is exactly the class of languages L that can be recognized within polynomial non-deterministic time, if you can build up such a computational tree of polynomial height. Okay, let's now look differently at it. Let's now look at this personally. So far it was a computation. Now suppose that we have some superhuman creature here, approver P, which intends to lead us to an accepting state. So it is his or her purpose. And then x belongs to our language L, if and only if it can succeed. So if it can lead us to the accepting state, like here, yes, then x must be in L. If he does not have any such strategy, then x must be outside of L. So, and in fact, it can be considered as a proof in some funny proof system. So we want to prove this statement x, that x is in L. And the way to prove it is simply to write a sequence of branchings in the protocol of this computation. It will be a sequence of L and R. L stands for go left, and R stands for go right. And when we have such a proof, what is important is that the length of this proof is polynomial in the length of x. And when we have such a proof, then the way to check that this legal proof is also very simple, right? This is a polynomial machine. So we can, once we have such a sequence, then we can simply simulate this machine and check that we really are at the accepting state at the end. Okay, so of course this proof system looks very funny, and if it would, if it would be the proof system which is inherent for the computational complexity, then nobody would think about it as of a proof system. But what actually happens is that when you talk about particular problems in NP, that is, when you talk about particular problems that can be solved by non-deterministic polynomial time machines, then with every particular problem you have a proof system which looks much more reasonable. So in a sense, PNP is exactly the question: can you always decide whether something is efficiently provable or not? Let me just give you a couple of examples. Okay, the most important example is satisfiability, of course. So you simply have just a propositional formula phi, where, well, it is some formula of propositional logic, that is, it is made only of propositional connectives like this. Well, it is not very sensible formula, of course. And we want to prove the following statement, that this formula phi is satisfiable. That is, it has at least one satisfying assignment. That is some sequence of 0 and 1s, which makes it true. Then in this proof system, of course, a proof is simply this assignment, and it is quite obvious how to check whether it is a legal proof or not. Just substitute this assignment to phi and check whether it is one or not. And the second example is also very trivial. Well, I don't mean that the example is trivial. It is trivial how to make a proof system out of it. So it is also a very important algorithmic problem, which is the graph isomorphism problem. You have a couple of ordinary graphs, well, for example, non-oriented, without loops and multiple edges, and you want to check whether they are isomorphic or not. Then, once more, a proof of this fact is simply the table which shows you how to make your isomorphism, and it is always easy to see whether this table defines an isomorphism or not simply by looking at all individual edges. Well, these examples are of course trivial, but they are very typical. If you have some interesting search problem, some problem from NP, then it can always be looked at proving something in this more or less trivial sense. Okay, great. And now, since Cook, Karp, and Levin's research, there were many other things in the complexity theory which were already not that trivial, and which led to very deep and very ingenious findings, and it even sort of changed the whole philosophy, or at least it attempts to change it. And I would like, in the rest of my talk, I would like to try at least to say something about it. And these are three major directions or deviations, if you like, because when we were talking about NP, all right, I forgot to say one important thing. It was on the slide, but I forgot to say it verbally. Right. So this verification predicate or verification procedure, it should not in general look like, well, having something with Turing machines. If you have, instead of this complicated and not very natural predicate, any polynomial time computable predicate, then we are still in good shape in the sense that we still have, of course, a language from NP. So you can verify, in fact, by applying to your statement X and to your proof Y any verification predicate A of XY as long as it is polynomially time computable. And these three directions actually, they challenge this classical scheme, and they challenge it in three different ways. Okay. Well, something is written here. And of these three things, I will be mostly talking about the third direction, simply for the reason that I am not competent enough to talk about interactive proofs and PCP. In this audience, there are several people who know much better, who know these things much better and proved very strong and ingenious results about it. And secondly, because I hope that I will take care of it. So that's actually okay. Anyway, don't answer, please. I just hope that it will happen. So, but at least I will say perhaps just a few words not about the definitions of these extremely important and interesting things, but simply to give you some idea how it matches into our scheme today. So interactive proofs are not really mathematical proofs. Suppose that your proof is long enough, is so long that you cannot even write it. Okay, well, we all know that there are some statements or results in the modern mathematics which are claimed to be exactly the same. And the way to prove interactively that you can prove some theorem, right, is like this. So you just say that, okay, my proof consists of these 1,000 lemmas. And you give statements, and it is relatively easy to check that these 1,000 lemmas, they really imply your theorem. I would prefer not to be specific here. You say so, okay. No. I'm not specific, I'm just talking about, well, I forgot what I'm talking about anyway. So let's go on. And it is relatively easy to check that these lemmas imply your theorem, but you cannot write their proofs altogether because they are too long. Okay, then the verifier, and it is important that our verifier is deterministic. I will say something about this later. Says, okay, I checked this, and now show me the proof of this lemma. Okay, the prover says, okay, this lemma is also very complicated, and we have to prove 10,000 other things about it before we prove it. Well, then the verifier says, show me this proof, and so on. And this is interaction, and if we have interaction in this fashion, and once more, it is very important that the verifier is some fixed polynomial time machine, and there is no non-determinism about this verifier. Then it turns out that in fact we don't get anything new here.
In what sense we get?
Everything which can be recognized by this interactive proof system is in NP.
No, but so if
Yeah.
actually verify every step or just verify step, choose what's exactly stated?
Well, there is no, well,
What exact statement?
well, I have to make several more definitions to make it exact, but the idea is that everything which you can prove interactively, right, can be also proved without any interaction. And, well, it's not a statement, of course, it's some intuition, but the reason for it is very simple, because our verifier is deterministic machine. Then the prover also knows how it's going to react to what he's going to say. So he simply says, okay, I know that you will ask me for the proof of the lemma number 738. I write it at the beginning. Then I know that you will ask for this statement. Here it is. Okay, that's what I give you. Now you can check it by yourself. That's why it is important that the verifier is some fixed machine. If there is some non-determinism in its behavior, then we get quite different things, which are also very interesting, but they are outside of my talk today. But it turns out that if the verifier may toss coins, that is, if we combine interaction with probabilistic, well, with randomness, then we get some much stronger class IP, which is much stronger than NP. Let me confine myself to saying that it is much stronger. Yes, it is polynomially bounded like it was before, but now it can also toss coins. Well, of course, I skip a lot of specific details. And here is the most canonical example, probably, of some statement which cannot be proved efficiently, but which possess an interactive proof. Well, that's actually was one of this example was one of the reasons to begin to work with this theory, and it is the graph non-isomorphism problem. So, right, we already saw that to prove that two graphs are isomorphic is very easy. You simply demonstrate the isomorphism. How to show that they are non-isomorphic, right? How would a normal mathematician approach this problem, and how it is approached actually. We have to find some set of invariants and prove using well, some heavy mathematics that these are complete, like it was with the knot problem, with other problems of similar nature in mathematics. Sorry?
You only need to show that they're complete to show that the graphs are equal, which then all the invariants. If you have a single invariant that is different, then they're different.
Yeah, yeah, no.
You don't need any completeness.
You don't need
the graphs are
completeness.
different. You just need a single invariant. Nothing but completeness. Any invariant.
Any invariant will do, yeah.
No. Why?
A single invariant is different for G1 and G2.
Yeah, but suppose all your invariants are equal, then I don't recognize it as a proof. No, then it doesn't prove anything.
Then you've only failed to prove G1.
Always you would be able to.
Yes.
You see,
Of course, we're interested in proving only your proof must convince me, right, that they are not isomorphic. And if you give me a complete,
It's single invariant.
if you have it, but if you don't have
Say
it,
to prove the two graphs are equal, you can only give the isomorphism if you have it. So
Yeah, I think he's right, yeah.
no.
you said that to show the two graphs are equal. You said that
No.
to show the two graphs are equal.
But what is invariant?
You just
What is
exhibit the isomorphism.
what is invariant? What is invariant? What is invariant? What is invariant?
Let's say the cardinality, for instance. The cardinality is different.
Right?
Okay.
Yes.
Then I'm
Suppose.
saying I don't need a complete
No. But suppose. Yeah. No. Or we don't have now any complete set of invariants for
But that's
graphs.
the same for showing the two graphs.
No.
are the same. You said that that's easy because you just demonstrate.
Yes.
Yeah,
But
you
here.
don't need an algorithm to always give it.
Yes. But here I demonstrate that they are equal, right, within just one scheme. It's one algorithm. You demonstrate a mapping from V1 to V2, right?
Well, if you have it.
Yes, if you have it. But
If you have an
here.
algorithm that's guaranteed to give it, you just run your algorithm. If it fails to give it, they're different. So I don't see any.
No. The difference is that this problem is in NP. This problem is not known to be in NP. Okay, there is no proof system which could prove you that two graphs are not isomorphic. Suppose that.
Number of possible isomorphisms is 2 to the n. Number of possible invariants is 2 to the n. And the all-powerful rule is 2 to the n powerful, but not 2 to the n powerful.
Well, what is actually? No. The question I think is what is an invariant?
So his algorithm is to give you the number.
Right.
Because it's not going to get very far.
Right. You can.
He said it's hard to prove that any two graphs are different.
Right. Yes.
To specify one
Yeah.
set of invariants that would work for
Yes.
all pairs of graphs that are
It's like in algebraic topology everywhere. You have to find an explicit set of invariants and show that they are complete. We don't have any such thing for the graph isomorphism. So people are working.
The same is true for certain
No. The proof is simply there is just one invariant to show that they are equal. Invariant, it is of course not the right word, but let's call it invariant. It is right the set of invariants. Okay. Anyway, I think we'll discuss it. We'll discuss it later. Okay. Good. So and anyway.
It's unknown, this problem is unknown.
No.
A priori he may be right.
Sorry?
So he may be right, and this is he's right. So we can't argue.
Yes.
If
Yes.
he knows he's right.
Yes. But it's not known.
It's unknown. It's unknown that you're right.
Right, and people all right, yes, and people are really working on it. But here is another way to show it, and it's a classical example, as I said. So and suppose I want to prove you that these two graphs are not isomorphic. So I suggest that you toss a coin, right? And depending on its outcome, you take one of these two graphs, G1 or either G2. You permute at random its vertices, and you give me this graph. And I promise to tell you where did this graph come from, either from G1 or G2. Then see what happens. If they are not isomorphic, then I will always be able. Well, it's a great example. That's if they are not isomorphic, then I can always do it because I have an unbounded computational power, and I can always see whether you gave me a copy of G1 or G2. But if they are isomorphic, then I cannot really cheat you. there is no way I can cheat you, because you show me, no matter whether you took G1 or G2, you show me the same probability distribution. And I really have no clue where did it come from. So if you repeat this experiment sufficiently many times, then the probability that I will be able to cheat you.
To cheat meaning what? What do you mean cheat?
Or to claim that graphs are not isomorphic, right? If they are really isomorphic. I'm trying to cheat you. I have two isomorphic graphs, and I try to prove the wrong theorem, that they are not isomorphic. Right? Then with this procedure, I can't really cheat you. If you repeat it n times, then the best I can do is 2 to the minus n, the probability of my success. Okay. Anyway, so I will skip what I wanted to say about probabilistically checkable proofs, and these are really beautiful and important notions, and quite unexpected. I really love them, but unfortunately I don't have time to talk about it. So they are sort of developed, they were developed after interactive proofs, and they use a lot of techniques from interactive proofs, but the direction is different. In interactive proofs, we were talking about proofs which are so long that one cannot write them down. Now, and well, in the modern mathematics, it's quite, of course, it's also quite a common thing. Now we have such a proof, but nobody can check it. So the bottom line is how to check proofs efficiently, but I really don't have time to talk about it. So I will actually now say at least something about feasible proofs. And the theory of feasible proofs is, in fact, something which is more mathematically oriented, in a sense, because probably for a mathematician, even arbitrary polynomial time predicates would be too much, not even to mention interactive proofs. Well, a proof must be a proof, a theorem must be a theorem, what we do in mathematics. And the theory of feasible proofs is exactly in this general scheme. The theory of feasible proofs, it deals only with natural, well, forget natural, it's another thing. It deals with proofs which really look like mathematical proofs. That is, it doesn't consider arbitrary polynomial time predicates here. It considers something which we would recognize as proofs. And it's also a beautiful theory which has been developed over maybe last 10 years, and it leads to many striking things. And this theory is also very robust in the sense that you can arrive at it from at least 3 different directions: proof theory, what we are doing today, and some other stuff. And you get well, and no matter from which direction you came, you get equivalent frameworks, you get equivalent things. In this sense, it is very robust, and it's of course a good sign. This means that we are talking about some real phenomenon, or not something which depends on the changes in definitions. And in fact, this theory deals with just the same complementary problem as we already saw for the graph isomorphism. If you remember, and I will try to find this slide, in which I finally succeeded. Right. If you take some NP problem, then it is some problem which is obviously in NP, and if you take its complements, then it becomes very hard to show, and it leads to interesting theories in many cases how to show that the opposite statement. And just the same happens with the satisfiability, namely, if you have a propositional formula phi and it is satisfiable, then what does it mean that a formula phi is not satisfiable? This means that no matter what we substitute there, we get zeros. And this means that its negation is a tautology. That is, it is a theorem of propositional calculus. So if we are working about propositional calculus, then our theorems must look like, must be tautologies. That is, the set of all of all propositional formulas which are identically true no matter what are P1 through Pn. And it is very easy to see, and it was observed rather long ago by Cook and Direkov, is that if we don't restrict ourselves, and if we consider arbitrary polynomial time predicated verification procedures, then we don't get anything very interesting from the mathematical point of view, namely there is an efficient proof system for the set of tautologies, of all tautologies, if and only if NP is equal to co-NP. Well, basically, the proof of this statement is on that slide. And the situation becomes very different if we are interested only in natural, in mathematical, in practical proof systems. And
you say this is a theorem, but it's again, look again, obvious, no?
Yes.
It's an obvious theorem, so
Yes.
it's not a
Yes.
theorem.
Well,
It's a theorem that is actually named, but it's
well,
obvious, yeah?
well.
No, this theorem is, you make the statement, so after discussion, we had it done in Spain, and everybody understood it, and yes.
Look at the year, it's 73.
No, but just,
It was not obvious.
come on. It's just, the name theorem, but you don't know how you can trust what you say, but our theorem we don't understand so obvious, yeah? This was very confusing. To make trivial statement, you call
Good.
the theorem. They make non-trivial statement, also call the theorem. And when you see the trivial, now you don't see trivial is also trivial. It's very confusing to the audience, yeah? You know, say.
Okay, it's not trivial, it's easier. No, it's better.
Just the definition, main conception was non-trivial phenomena. Once you said it, just
Okay, good.
it seems again. I'm not
Okay,
an expert.
okay. In the way I put these things, it is really an easy observation. If you remove all previous slides, then it becomes an easier. Sure. Good. Okay. Anyway. And the theory of feasible proofs is actually deals actually with these things. When we are talking of computational complexity, then our major question is what can we compute if our computational tools are bounded, are limited. If we have only polynomial time machines, which problems can we solve? And the theory of feasible proofs in fact deals with the same kind of questions with the same kind of problems. Suppose our computational tools are still limited. For example, we are talking only about polynomial, we have only polynomial time machines. What can we prove if we are allowed to use in our proofs only concepts that are polynomially time computable? Which proofs can be made feasible in this sense? And here is a very good example, also a canonical example, Fermat's little theorem, which shows that computability and probability in feasible words are really different things. And Fermat's little theorem, let me write it this way: if A is a prime, it does not have any non-trivial divisors, then this thing, then x to the a minus 1 is equal to 1 modulo A. Right. So, and everything which is involved in its statement, all these functions are polynomially time computable. The only thing which can raise some doubts is, of course, this function, exponentiation, but it's actually not very hard to see how to do it. You simply write A as its binary expansion, and you do it. But when it comes to the proof, then things look really different. Namely, in order to prove, well, how to prove this theorem? How is this theorem proved? So, and the first statement is let M be the order of the element X in the multiplicative group modulo A. But what is the order? How to prove that X has an order? And the only proof we can show is to start powering X, take X squared, X cubed, and so on until we have two identical numbers, X to the M1 and X to the M2. Then X to the M2 minus M1 will be 1. But this is not a feasible argument, right? You have to search through A possibilities, which is exponentially long. Which is, you cannot do it. And it turns out that, in fact, not only this argument is not feasible, but in fact, Fermat's little theorem cannot have feasible proofs unless we can destroy all the modern cryptography. Well, it was almost destroyed by the previous talk, of course, already, because we know that factoring is easy if you can do quantum computers. So the real purpose of this section is how to destroy all the modern civilization, all the banking systems, either construct quantum computer or make a feasible proof of Fermat's little theorem. It's another viable approach to this problem. Okay, anyway, so 5 minutes. 5 minutes, yeah. Okay, good. Good. So, and let me at least show you some examples of proof systems we are interested in this theory. And the first example are Frege proof systems. And these are ordinary textbook proof systems, in fact. So if you take any textbook on mathematical logics, then what you see there is a Frege proof system for proving tautologies. And it is important that all these proof systems are equivalent, well, because different textbooks usually use different proof systems, and they correspond to the complexity class NC. Well, for those who don't know what is NC, never mind. And if you want to make a proof system which corresponds to our central class P, then we must add to the Frege proof another feature, namely we have to allow to make abbreviations. If you have a long formula, that's what mathematicians do actually. If you have a long formula A, then, and if it's going to repeat in your proof many times, then you don't really repeat it. You introduce a name for it and use this name instead of the formula itself. That will be extended Frege proofs. And another proof system, it's just a different example, is the polynomial calculus, and it actually supposes that you have some set of polynomials f1, f2, fm, and you want to generate the ideal by you want to prove that something is in the ideal generated by this polynomial. Then what will you do if you have a sheet of paper and a pen? You will just try to prove new elements which are in this ideal, and this is the proof system exactly to do it. These are simply the definition of an ideal. You take the closure under these two simple operations. Okay. No. No.
He said it's correct.
It's a good remark. Well, I skipped, of course, many technical details in my talk, and in this theory we are in, no. If the question is here, I will give the answer. In this theory, we are interested in the Boolean situation when x squared is always equal to x, and it is not so hard to see that if you have these elements in your ideals, then Nullstellensatz does not require taking the radicals. Okay, good. Anyway, in this theory we try to prove lower bounds, and I decided that in this talk that would be ridiculous to give a chart of these lower bounds. Everybody interested can look at this great recent survey, what we can do in this theory, what we cannot do. And there is one more link between computational complexity and proof complexity, because the techniques which are used here, they are mostly borrowed from the computational complexity, and it is one more proof of the thesis I'm trying to make today, that both proofs and computations, when we try to show something about them, they require the same kind of techniques. And okay, and the only other thing I wanted to say in this talk is really my personal motivation to be interested in this feasible proof theory. And the reason, actually, these slides, they are very vague and random anyway, so I will skip them. I will just tell you only a few words. That if we study the probability of this question in different logical systems, then it turns out that there is a natural system in which most of partial results we have so far, they are provable there, so it makes sense to study this system. And there are approaches to showing that P versus NP is not provable in the proof system, and moreover, there are, I think, grounded hopes that even no matter whether we can do it or we cannot do it, that there will be some byproducts. There are already some byproducts which really help us to better understand the nature of this problem. So this is one more link, but I really don't have time to talk about it, and maybe it's even better because it's very vague. It's very unfinished. It's work in progress. Okay. Много